Hey, so this is a short video I wanted to make explaining the two different ways of representing vectors in three dimensions. I've evolved over the years from a wire model with a straw for the vector to various wood contraptions, and finally kind of went to SketchUp a couple of years ago, and now I'm making a video of it because it's getting a little cumbersome to actually run SketchUp. What I wanted to start with was the direction angle representation. As you remember, these are the alpha, beta, gamma angles that define a 3D vector. And you can kind of see what I'm talking about when I say you're allowed to use this right triangle trig for these things, because you can kind of see, so here's the vector f here, right? And f is drawn within a rectangular prism. And as you rotate around, you can kind of see the vector f and the different planes that are formed by connecting f to the x, y, and z axes, right? So that forms a plane here. And when you rotate it, you can convince yourself pretty clearly, just graphically, that, yeah, there's a right angle at the corner of each of these planes. And this is why the cosine relationship applies to these vectors when you've got this alpha angle here going between the force vector and the x-axis. Then, because this is a right angle, you can easily deduce that that the cosine of alpha is the adjacent over the hypotenuse, right? So cosine of alpha equals fx over f, and therefore fx is f times the cosine of alpha, right? And you can rotate things around and get the same, the same representation for the same relationship for beta, where again you see that that angle beta there is closer to 90 degrees in this case to the y-axis, and f again, or fy over f is going to be the cosine of beta, right? Because you've got fy as being the adjacent to the angle and f as a hypotenuse. And lastly, you've got gamma, which is the angle to the z-axis, and again, fz is adjacent to gamma and f is a hypotenuse. Got another right angle up there in that left corner. So, so therefore, fz over f is the cosine of gamma, or fz equals f times the cosine of gamma. So there you have the direction angles, and these are posted. If you do have SketchUp on your machine, you can kind of play around and rotate these things. But I thought this video would be sufficient. The other representation is the projection angles. These are a little more confusing, perhaps, just because it's not consistent with each component, but it also makes sense in its own way. The interesting thing about the projection angles is you're making a vertical projection straight down to the xy plane beneath that force vector f, right? You don't see that in the direction angle one. The direction angle is just making these connections to the xy-z axis, not dropping a projection line straight down to the xy plane, right? That's missing in this one, but you do see it in the projection angle one. So what we're doing is like we're casting a shadow from straight overhead of f onto the xy plane, giving us this line f prime, right? And because we're calling this angle to the horizontal theta, again, you have another right angle there, right? And so therefore, the cosine of theta is going to be this f prime value divided by f. Or you could say that, f prime equals f times the cosine of theta. Now, we never really need f prime for anything in our Cartesian representation. It's just an intermediate step to getting fx and fy, because once you have f prime, you can look at this thing from above, and the label's a little bit missing, but f prime is this line going on the back plane from the left corner, lower left corner, to the upper right corner of the back plane. There's a perspective thing going on here, which is cool. and that f prime is the length of this base of that vertical triangle. It also turns out to be the hypotenuse of this triangle, and if we have this angle phi labeled, which is the angle between that projection and the x-axis, then we can make that same relationship. Fx now is adjacent to phi, f prime is a hypotenuse, so fx over f prime is the cosine of phi, or fx equals f prime cosine of phi. Likewise, on the y-axis, once you have f prime, then and you know what phi is, you can show that fy is the same on the other fy here. That this side of the box is the same as this distance here, which is the opposite of the angle phi. So that is the sine. In other words, fy over f prime is going to be the sine of phi. So therefore, fy equals f prime sine of phi. And finally, for the z-axis, fz equals well, for the z-axis, there is no need to use f prime. You just can realize that the height fz, the distance fz, is the same as the side of this side of the vertical triangle, which again is opposite of the angle theta. So fz over f equals the sine of theta. So therefore, fz equals f times the sine of theta. So a little complicated, but if you can kind of visualize these things in your head in a similar way, you'll find it's pretty easy to keep track of all these different components. And like I said, you can download these and mess with them if you like. But this video should be enough to hopefully explain it to you. If you have any questions, just let me know. Thank you.